That was called momentum, and momentum is really a quantity that helps us solve many different kinds of problems. Momentum. And momentum is simply defined as the product of mass and velocity. That's what momentum is. It is the product of mass and velocity. The symbol for momentum is a P, and you need to have a vector symbol over P. If correctly written, you need to have a vector symbol over P. And as you can see, P is mass times velocity. And is momentum a vector or a scalar? It's a vector because velocity is a vector. What's the direction of momentum? The same as the direction of velocity. What would be the unit of momentum? Let's put the units of mass and velocity together. Unit, yeah, it's kilogram meter per second. Not kilogram per meter per second, but kilogram times meter per second. So that is the unit of momentum. Now, clearly the diagram shows you that the direction of momentum and the direction of velocity are the same. That's what it shows. Again, momentum is a vector which has the same direction as that of velocity. So, from the chapter of scalars, work and energy, we are back into a chapter of vectors. So we'll have to resolve again, find components again. And as I told you, the unit is kilogram meter per second. Conservation laws are very important in physics. We've already done one conservation law. It's the conservation of energy in the last chapter. Here we have the conservation of momentum. The conservation of momentum comes with a condition, a very important condition, that no external forces must act on a system. That's an important condition. Momentum is conserved only if no external force acts on a system. So when we say it's conserved, we are saying that it doesn't change, right? That means if you take the differential of momentum with time, it's going to be a, what is dp by dt going to be if p is constant? If p is constant, what is dp by dt? Thank you, 0. dp by dt is 0 because p is a constant. If you take the differential of anything, because it doesn't change with time, right? That's why understanding is key, not writing down the equations, understanding. If momentum is constant, that means it does not change with time, which means when you take dp by dt, you're going to get 0, right? So that's what I'm trying to write. dp by dt, it can be written as d by dt of mass times velocity, because p is mass times velocity. And whenever you take the differential, you take the constant out. What's the constant there? You have mass and velocity. What's the constant? Mass is the constant, so that's taken out. And then you have dv by dt. What's dv by dt? Change in velocity over change in time. Acceleration. dv by dt is acceleration. So we get Newton's second law of motion from the definition of momentum and conservation of momentum. See that? Because we've already seen that net force is equal to mass times acceleration. So now we are saying dp by dt is the same. dp by dt is mass times acceleration. So put them together. Because we know that net external force is ma, compare the two. So when you put them together, you get a new equation that the net external force is dp by dt. That should make sense. Is that making sense? Just put the two together. Net external force is dp by dt. So now if I set the net external force to 0, surely dp by dt is going to be. So that's why I told you it comes with a condition. So if net external force is 0, then dP by dt is definitely 0. And if dP by dt is 0, that means P does not change, or rather P is a constant. So that is the principle of conservation of momentum. Momentum of a system is conserved if no external forces act on the system. And I can ask you this on the exam, what is the condition? And I expect all of you to give the condition that there should be no external forces acting on the system. Let's take a particular case of a collision between two objects. The two objects have masses m1 and m2, and they are moving with velocities v1 and v2. As you can see, if v1 is greater than v2, then they're going to collide, right? Assuming that they're moving along the same line, because if this is moving faster, it's going to collide. Now, after collision, their velocities are going to be redistributed. Here is supposed to be v1 prime and v2 prime. So they have new velocities. Will their masses change? No. So let's try to apply the conservation of momentum. So that's before and that's after. And they did collide for a certain time. That means they were in contact for a small amount of time, right? That's what you mean by a collision. Let that time be delta t. They are in collision there. And when they are in collision, are they exerting forces on each other? When two objects are colliding with each other, are they exerting forces on each other? Would you call that an external force? No, that's an internal force within the system. If they are colliding, I go and kick them, that's an external force. You see the difference? So in this case, how do you read F12? What does that mean? Force applied?
Force on 1.
Force on 1 due to 2 should be equal to,
Force on 2 due to 1.
which law is that?
That's
Newton's third law. But shouldn't there be a negative sign? Because for every action, there's an equal and opposite reaction. So the object 1 exerts a force on 2, and 2 exerts an equal but opposite force on 1. So it comes with a negative sign. And like I told you, this is an internal force. So these are internal forces. Okay, net external force must be 0. Start with that again. Therefore, momentum must be a constant. That is the initial momentum, isn't it? That's the initial total momentum. Take the momentum of each and add them. m1v1 plus m2v2. That's the total momentum of the system. Should be equal to the total momentum after collision. That is the conservation of momentum. Simple enough. So that means total momentum before is equal to total momentum after. You'll be applying that equation several times with small changes depending on the problem of conservation of momentum. It's a recoil of a rifle. Well, everybody knows that when you use a rifle, try to fire a bullet, you have the butt of the rifle pressing against your shoulder, right? Why? Because it's going to recoil. Now, we're going to apply the conservation of momentum here. But before we do, let's see whether you can think. What's the bullet doing inside the rifle before firing? Is it dancing around? It's not moving. What's its momentum? Before firing, 0. And the gun, nobody is shaking the gun before you fire it. You're trying to hold it still, right? So what's the momentum of the rifle? 0. So before firing, both the rifle and the bullet have 0 momentum. So total momentum before firing is 0. Is that clear? Because both of them are not moving. And then the bullet comes out with a certain velocity, and so it has a momentum. And then the gun, if you're not pressing it against your shoulder, right? Just imagine you're just holding it free. It goes back with a certain velocity, so it has a momentum after firing. So if you add those two momentas, it must equal 0. Is that clear? Because the total momentum before firing should be equal to the total momentum after firing. That's what you're going to see. Okay, the masses is the velocity. You see the velocities with which they come out initial momentum is equal to the final momentum. Pi is equal to Pf. Okay. Initial momentum of both is 0. What's the final momentum of the bullet? Isn't it mb times vb? Yeah? Isn't that the momentum of the bullet? Product of its mass and its velocity, right? Okay, plus mr times vr. That's the conservation of momentum there. Rearrange and try to make the velocity of recoil the subject. Simple math, and you get this. Oh. Now, take a careful look at this equation. What does the negative sign show? Direction. Yeah, the rifle moves opposite to the direction of the bullet. Okay, what can you say about the magnitude of this? Is this going to be small or large compared to the velocity of the bullet? That's a silly question. Small. Why? Mathematically, why? What do you have in the denominator? The mass of the rifle, which is considerably larger than the mass of the bullet, isn't it? So this ratio here is much smaller than 1. You know what I mean? That's why the velocity of recoil is going to be much smaller than the velocity of the bullet. Now that's just one application of conservation of momentum. Rocket propulsion is another application of conservation of momentum, where again the initial momentum is 0, isn't it? Both the gases inside and the rocket, both are at rest initially. And then on launching it, the gases come out with a certain velocity, right? And a particular mass comes out per second. So you can get the momentum of the exhaust gases coming out in 1 second. And then the rocket has to go up. It's exactly like the recoil of a gun. So that's another application, and there are many applications. But let's take a look at collision now. If you have, the previous case that we talked about is really silly. You remember the case where you had two objects? Because that was collision in one dimension. Right? Both the objects were moving along the x-axis, and after collision they continued moving along the x-axis. That doesn't happen, really. Normally what happens is you might have two objects colliding on a table, the top of a table, let's say, and they collide. And do you expect them to continue moving along the same line after collision? No. You expect them to sway away, isn't it? So that's collision in 2 dimensions. So let's take a look at that and see how that's going to affect it. Okay. Here you can see the initial velocities, v1 and v2. They are along one line because they can always be in one line before collision, right? Joining 2 points, you always get a straight line, right? Okay. But after collision, velocities and the directions are now given. Okay. Let me stop it right there. So that's a diagram that you need to take down and try to apply the conservation of momentum both along the x and the y axis. What is the component of this one going to be along the x-axis? Isn't it going to be m2 v2 prime cos theta 2, right? Okay, what about the vertical components? This is going to be m1 v1 prime sine theta 1, and this is going to be m2 v2 prime sine theta 2. Now what we're going to do is apply the conservation of momentum both along the x and the y. Can you write the equations individually? Go ahead. What's the total momentum along the y-axis before collision? What's the total momentum about the y-axis before collision?
0.
Yeah. So when you take the vertical component, I don't remember which one I wrote first. If I did write that one first, then it's going to be 0 is equal to the cos. Add the cos's. You can do it on your own, write it. You need not copy. That's the complete diagram. Okay, along the x is what I wrote first. Along the x is m1 v1 plus m2 v2, right? Is m1 v1 prime cos theta 1 plus m2 v2 prime cos theta 2. Now try cramming this. You go crazy. Try understanding it. It's easy.
Like playing pool.
It is. It is. Okay, along the y-axis, 0 is equal to, there you go. And if you have two equations, can't you solve two unknowns? I mean, solve for two unknowns? Yes, you can. So you can find v1 prime and v2 prime if everything else is given. So that will simply be solving the two simultaneous equations. And it's not supposed to be tough. Now, where did that sound come from? It's a part of the kinetic energy, which has got converted into sound. And obviously, when two objects collide, heat should be produced, right? Heat, sometimes you have fire. Isn't that how the early man produced fire? Two stones. Where did that energy come from? It's kinetic energy being converted into heat. So when you think about collisions, you're always going to think about there's always going to be loss of kinetic energy. That's what you're going to think about. But it's not true. Because if two objects do not touch each other, they can still said to be colliding with each other.
Doesn't make no sense.
It makes in physics, and I'll tell you why. If you have a nucleus here, what's the charge of the nucleus? The overall total charge of the nucleus, positive. And if you have, let's say, another positive particle, maybe the proton, coming at it, it's fast moving, right? So it has a lot of kinetic energy. But as it approaches, you know its kinetic energy is going to get converted into potential energy because of the force of repulsion. Are you with me? So it's going to slow down, and at one point it's just going to stop and return. That is a collision. They did not touch each other. You know that as it approaches, the force of repulsion gets stronger. Are you getting what I'm saying? So as it approaches and maybe comes very close, but it returns without actually touching, that is a collision in physics. Now that is called an elastic collision. Magnetic poles, yes, charged particles. So you have to clear your thinking and say, okay, collision does not always mean that two objects have to touch each other. But I'm with you. In the macroscopic world, which is the world that you can see with your eyes, collisions always happen when objects touch each other. But in the microscopic world, nuclear particles and all that, collisions could occur without them actually touching each other. So now we have two types of collisions. One is called an elastic collision. That's where they really do not touch each other. That is an elastic collision. And the next is inelastic collision. There are two types of collisions. And we are used to inelastic collision. What's the difference? In both these types, momentum is conserved. I want that to be very clear because students get confused for, I don't know, nothing. In both of these cases, momentum is conserved. Is that clear enough? Momentum is conserved. But in the case of elastic collisions, kinetic energy is also conserved. So in an elastic collision, you have both momentum and kinetic energy conserved. But inelastic, you only have what is conserved. In an inelastic, only momentum. That's the big difference. Okay. So in an elastic collision, both momentum and kinetic energy are conserved. I'm trying to write it on both sides. And in inelastic collision, only momentum is conserved. That's the difference. Okay, apply the conservation of momentum. Instead of using M1V1, I'm using MAVA. That doesn't make it confusing, does it? It's just the two objects are A and B. What's that? Isn't that the conservation of momentum which I've written? Okay, so if we are looking at an elastic collision, kinetic energy is also conserved. And we know kinetic energy is 1/2 times mass times velocity squared, isn't it? So I'm going to apply the conservation of kinetic energy there. The kinetic energy of the first plus the kinetic energy of the second before is equal to the kinetic energy of the first after plus the kinetic energy of the second after. Okay, that makes sense. So I've written the conservation of momentum and the conservation of kinetic energy. What type of collision are we talking about right now? Is it elastic or inelastic? Elastic, because I'm assuming both are conserved. And now there is some math to go from the first equation. I'm going to take MA common. And you know what I did? I have taken this to the left-hand side, and so that becomes negative, isn't it? And then I separated the MA. Do the same with MB, but this time the sign of this one changes because that goes to the other side. Are you with me? Be careful. Look at this and look at this. There's a difference. Because this one went to the left side, its sign changed. This one went to the right side, its sign changed. That's equation 1. I'm going to do the same with equation 2. First of all, of course, I can cancel the halves and then do exactly what I did. It's better to understand and then write. I'll give you the time. Okay, I'll give you the time to understand and then write. Then you will know what I'm trying to do. Now, do you know that in math you can split this up into two factors? If you have a squared minus b squared, you can write it as a plus b times a minus b. I'm going to do that. Okay, so I'm splitting that up into a plus b times a minus b. Same thing on the right side. I'm going to call it equation 2. And then I'm going to divide equation 2 by 1. If I divide equation 2 by 1, what's going to happen to the left-hand side? Will the MA's, I'm dividing this by this, will the MA's get cancelled? Yes. And will not this also get cancelled with this? When I'm dividing, okay, same thing happens on the right side. The MB's cancel out and this cancels. Okay, that's what I'm doing now. And I get a very interesting equation, which I'm going to rearrange and put it in this format and let you write now. And I want to see who can remember. Can you give me one statement for this? Don't read it as VA minus VB. I know how to read that. But in physics, this particular quantity is called something. What is it called? It's not called change in velocity. It's not delta V. You're all trying. It's called the relative velocity. The relative velocity of one object with respect to another. If one is moving at 50 miles per hour, the other is moving at 30 miles per hour. What's the relative velocity of one with respect to the other? 20 miles per hour, right? So, in an elastic collision, we have proved that, look at this carefully, that the relative velocity before collision is equal to the opposite. Do you notice that it's opposite? Is equal to the opposite of the relative velocity after collision. As an example. And it does not depend on the masses. Do you notice that? It does not depend on the masses. You have two objects. You don't care what its mass is. This is moving at 5 meters per second before collision. This is moving at 2 meters per second before collision. All right? After collision, if I tell you that the first object is moving at 4 meters per second. 4 meters per second. Can you tell me with what velocity the second object is moving? I've not given you the masses because it does not depend on the mass. So it's a cool equation. 5 minus 2, isn't it? Should be equal to, be careful there, should be equal to VB prime unknown minus 4. So that's 3 and that is 7, isn't it? What is interesting is that's totally independent of its masses. This could have been 100, this could have been 1. You realize what I say? It could have been 5, or I don't know, whatever it is. Totally independent. So that's going to be very powerful when you try to solve problems. Keep that in mind. That equation is very important. Wait. In this equation, anybody knows what's the value of E? In this equation? 1. So, if the coefficient is 1, you call it an elastic collision. if it is anything else other than 1, are you listening? Anything else. Do I mean greater than 1 or less than 1? Common sense.
Anything.
Less than 1. The maximum value of E is 1. Anything less than 1, it's inelastic. And the worst case, I don't know why I said it's the worst case, but if E is 0, and you're looking at me, listening to me, if E is 0, then it is called a perfectly inelastic collision. Perfectly inelastic. I want that to be very clear. Wait, if E is 0, what happens to the right-hand side?
0.
What does that mean? That means the two objects stuck together. Definitely. Because if you have to get the difference as 0, that means there's no difference, which means both of them are moving with the same velocity. Are you with me?
Yeah.
So if you take a ball made of clay or whatever and throw it on that wall, it's going to get stuck on that, right? That's a case of perfectly inelastic collision. Any case where two objects ram into each other and get stuck and then move together, are you listening? That is perfectly inelastic, means maximum kinetic energy is lost. I hope you heard me. Perfectly inelastic means maximum kinetic energy is lost. So now I've given you the difference between perfectly elastic and perfectly inelastic. Okay, E is equal to 1 elastic, E is equal to 0, perfectly inelastic. Normally E is between 0 and 1. That sensible enough? Are we looking for making E as close to 1 as possible? Yes. Wait, if you drop a rubber ball on the floor, will it come back exactly to the same height where you dropped it from? You're not throwing it to drop it.
No.
So is that collision elastic or inelastic? Inelastic. So it lost kinetic energy. That's why it could not come back to the initial potential energy. Are you getting it?
Yeah.
What about if it's a steel ball, a tiny one, just to make your thinking clear, and drop it? Many a time it will bounce back to a greater height than the rubber ball. We're talking about a concrete floor. A small steel ball, think. It will bounce back. Shows that collision is more elastic than between rubber and concrete. Again, think about dropping that steel ball into sand. All the kinetic energy is lost. Are you?
So is that perfect? That wouldn't be perfect inelastic, right? Or
Well, because the sand is a huge object and you can't really say it's moving, along with it. But, well, technically it's perfectly inelastic. Impulse is the next topic, impulse. And this word comes from, I think, biology, where you would have heard of reflex action. Have you heard of a term called reflex action? Impulse? I always give this example of somebody pricking you from behind with a pin on your neck. And would you go in style and tell, hi?
no.
Yeah, no, you don't get, maybe dad, mom, you don't know who it is. It's immediate. It's a huge force acting for a short time. That's what an impulse is. It's a huge force on the cheek or the head, I don't know wherever you can hit that person. But the contact is for a very small time. Is that clear enough? And it's a huge force. There are many other examples. Trying to hammer a nail into a piece of wood with a hammer. Nobody goes like, no. It's like, is that? Yeah. The contact is small. Hitting a tennis ball with a racket, there are thousands of examples.
Haymaker.
The time of contact is small. That's what I'm trying to say. Punting the football, you name it. So in these cases, it's like, now let's get the logic behind this. The force is acting for such a small time, correct? The time is so small that we cannot actually calculate the force like we normally do. How do we normally calculate the force? Mass times acceleration. We can't. Because the time of contact is so small, it'll be really silly to say, let me find the acceleration. So scientists decided we'll call this an impulse. We cannot calculate the time, it's so small. And the force, think about the force. Is it a constant force? Nope. The force goes from 0 to a peak to a 0, if you're with me. Are you getting it? It's like within that short time it goes boom, boom. So now you have to talk about an average force. An average force. And you multiply the force with the time. That's called the impulse. So what's impulse? Impulse is the product of the average force multiplied by the time. I hope you got that clear. That's why I brought out the idea of the average force. So that's what impulse is. Okay, the definition, impulse is a large force acting for a short time. That's the situation. And don't we know that force is dp by dt? Come on. Again, I'm going to give you time to write if you can get this. F is dp by dt, rearrange, dp is f dt. Take the integral. Be with me, take the integral on both sides. T1 to T2. Okay, and this is called impulse. So now you see that the change in momentum, isn't that what it is? Change in momentum is called impulse, represented by the letter J. So when you see J, that means it's impulse. And it is integral f dt, T1 to T2. That's the formula. Now, there are two equations there. Take a look at that carefully. There are two equations for impulse. One, impulse is force multiplied by, integral f dt, right? Or impulse could be just change in momentum. So there are two equations for impulse. One here and the other here. What were you talking about? Work? No, work is force times displacement, not force multiplied by time.
Yeah, but you get the integral, but then
That's integral of f dx.
yeah, nothing. I get it.
Because it looks like a rabbit, it doesn't mean it's a rabbit. Oh my God, that's on. I tell you that the force goes from 0, peaks, and then goes back to 0 within a short time. Did I tell you that? And if you watch carefully, you see that I'm going to find the average force, which is right about here. Hello? Be with me. That's the average force. That's a maximum, 0. So the average force. And technically, somebody tell me, in math, and everybody knows this, in math, when you take the integral of f dt, what is that for this figure? Area. Okay. So I'm going to find the area, but I'm going to find it in a different way. Watch. So that's the average force, and that is given by the area. The area of which one? Actually, you were supposed to find the area of this figure, see? But, see, what I've done is I've taken the average force and I've found the area of the rectangle, which is exactly going to be the area of this figure. If you notice, you see, if you divide this into two parts here, can you see? You see this part has this area. This other part has this area. Anybody with me? Yeah. So that's what we're trying to do. So I'm going to give you another formula now. I'm going to say, yes, that's just average force multiplied by change in time. See what happened? So you can either write it as integral T1 to T2 f dt, or you can say technically it's equal to the average force multiplied by the time. Because integration means finding the area. Is that clear enough? Okay, so now there are three ways of finding the impulse. Center of mass. We're trying to change a two-object problem into a one-object problem. That's what we're doing. I just picked this one to kind of make it interesting. If you throw this, what do you call this? A wrench, right? If you throw it and it's spinning, although the object is spinning, you see that there is a certain point, this point, which is actually moving in a parabolic path. See what I'm saying? That point is called the center of mass. That point is just following this trajectory there. But the whole thing is spinning. But how do you find the center of mass of two objects? So I'm going to have one object here, and I'll put the second object also on the x-axis. The first one is at x1 from the origin. Second one is at x2. Those are the distances. And their masses are m1 and m2. Definitely the center of mass of the system should be between them, isn't it? Everybody knows it should be on the line joining them. The center of mass of two objects will always be on the line joining them. And use your common sense and tell me, will it be closer to the heavier one or closer to the lighter one? Heavier one. Because essentially that's the point where you can balance it. You see, that's the point. So the center of mass is always going to be closer to the heavier one. But how do we actually define it? It's simple. Just take the product of the mass and the distance, add them up for each, divide by the total mass. That's how you find the center of mass. Done. So you take the product of each mass with its distance. See how it works? So it's m1x1 plus m2x2 divided by the total mass. That's it. So 2 points. Center of mass is always going to be on the line joining them. This is how you calculate.